Hello everyone, welcome to part 2 of Unit 5 on cloud applications and cloud simulators. We move to cloud simulators, which are tools used to model and test cloud computing environments virtually. In this section, we will study important simulators such as CloudSim, GridSim, GymSava, and GreenCloud, which help researchers and developers analyze cloud performance, resource allocation, and energy efficiency without building real cloud infrastructure. Next, the need for cloud simulation. Suppose a startup wants to launch a video streaming service. Before investing money in real cloud infrastructure like Amazon Web Services, they can first use CloudSim to simulate thousands of users watching videos simultaneously. Using the simulator, they can model virtual machines, bandwidth usage, CPU load, and storage requirements. Based on simulation results, they can optimize their cloud architecture, improve performance, and estimate operational cost before actual deployment. So, cloud simulation helps reduce risk, save cost, and improve system planning. What is a cloud simulator? A cloud simulator is a software tool used to simulate cloud computing environments virtually. It helps researchers and developers test cloud applications, analyze performance, and study resource management without using real cloud infrastructure. This reduces both cost and risk. Cloud simulators allow users to model cloud systems, perform experiments, and evaluate different cloud configurations. This slide also lists some popular cloud simulators. CloudSim is used for general cloud environment simulation. GreenCloud mainly focuses on energy efficient cloud and network simulation. iCanCloud is used to study different cloud policies and pricing models. EmuSim combines both emulation and simulation techniques. Other simulators like Network Cloud Sim and Cloud Analyst are also used for specialized cloud research and analysis. Introduction to CloudSim. CloudSim is a cloud simulation toolkit developed by the Clouds Laboratory at the University of Melbourne. It is mainly used for modeling and simulating cloud computing environments for research and performance analysis. CloudSim supports components such as data centers, virtual machines, or virtual machine cloudlets, which represents tasks and brokers that manage resource allocation. It allows researchers to simulate cloud workloads, virtual machine provisioning, and scheduling policies without building real cloud infrastructure. CloudSim also supports advanced features such as power-aware data centers, federated cloud environments, and network topology simulation. Overall, CloudSim is highly customizable and widely used for cloud computing experiments and performance evaluation. Foundational principles. This slide explains the foundational principles behind CloudSim. The first principle is abstraction layer. CloudSim provides a simplified virtual environment for modeling cloud systems without dealing with the complexity of real cloud infrastructure. The second principle is modularity. CloudSim has a modular architecture, which means users can easily customize components such as scheduling algorithms, resource allocation policies, and cloud configurations. The third principle is event-driven simulation. CloudSim works using events like virtual machine creation, task execution, and resource allocation. These events trigger actions within the simulated cloud environment. The final principle is realism. Even though it is a simulator, CloudSim tries to imitate real cloud environments by modeling factors such as network latency, workload patterns, and resource scheduling. So overall, these principles make CloudSim flexible, customizable, and suitable for cloud computing research. CloudSim architecture overview. This slide shows the overall architecture of CloudSim. At the top is the user code layer where users define the simulation scenario, application requirements, and scheduling policies. The user or data center broker acts as the mediator between the user and the cloud resources. The next layer is the CloudSim layer. This is the main framework layer. It contains important simulation components such as cloudlets and virtual machines. A cloudlet represents a task or application, while a virtual machine represents the computing environment where the task will run. Below that, we have virtual machine services. This layer manages cloudlet execution and VM management. It decides how tasks are executed inside virtual machines and how VMs are created, managed, and destroyed. The next layer is the cloud services layer. This layer handles virtual machine provisioning and allocation of important resources such as CPU, memory, storage, and bandwidth. Then comes the cloud resources layer. It includes data centers, cloud coordinators, sensors, and event handling. These components represent the actual cloud infrastructure in the simulation. The network layer manages network topology and message delay calculation. This is useful for studying communication delay between different cloud components. At the bottom, we have the CloudSim core simulation engine. This is the foundation of the entire architecture. It manages event scheduling, simulation time, communication between entities, and overall execution of the simulation. So overall, this diagram shows how CloudSim separates user requirements, cloud services, resources, networking, and simulation control into different layers for easy modeling and experimentation. This slide explains a real-world example of how CloudSim can be used. Suppose a startup wants to test a new cloud application that may be accessed by 10,000 users simultaneously. Instead of deploying the system directly on a real cloud platform, they first simulate the environment using CloudSim. In the simulation, virtual machines are created to represent cloud servers. Cloudlets are created to represent user requests or application tasks. The simulation is then executed to observe system behavior. After running the simulation, the startup can analyze important factors such as resource utilization, system performance, network behavior, and operational cost. This slide also explains that the user defines the cloud scenario, application configuration, and resource requirements. A broker is used to manage virtual machine allocation and task scheduling. At the back end, CloudSim uses discrete event simulation principles to handle event queuing, time progression, and resource state management. So overall, this example shows how CloudSim helps organizations test and optimize cloud systems before real deployment. Operational mechanism. This slide explains the important entities used in CloudSim and their functions. First is the data center. A data center contains multiple hosts and behaves like a cloud service provider. It receives requests from brokers and creates virtual machines on host. Next is the data center broker. The broker acts on behalf of the user. It sends virtual machine creation requests to data centers and assigns cloudlets or tasks to suitable virtual machines. Then comes the host. A host is a physical server inside the data center. It manages virtual machine creation, destruction, and allocation of resources such as CPU, memory, and bandwidth. The next entity is the virtual machine. A virtual machine behaves like a software-based computer that runs applications. It shares the host resources among different running tasks. Finally, we have the cloudlet. A cloudlet represents a task or application workload inside CloudSync. The scheduling policy in the broker decides how cloudlets are assigned and executed on virtual machines. So overall, these entities work together to simulate resource allocation and task execution in a cloud computing environment. Understanding GridSim. This slide explains GridSim, which is a simulator designed for grid computing environments. GridSim provides features such as resource management, job scheduling, and network modeling for distributed systems. It served as the foundation for developing CloudSim. CloudSim uses several GridSim components for functions like network simulation and resource allocation. Later, CloudSim extended GridSim capabilities by adding support for virtualization, cloud data center modeling, and energy-aware simulations. So overall, GridSim can be considered the base framework upon which CloudSim was developed. Let us understand the GridSim working diagram. On the left side, we can see different users or client applications such as Java clients, .NET clients, and C++ clients. These clients submit tasks or jobs to the grid computing environment. All these requests are collected and converted into tasks that needs to be processed. These tasks are then sent to the control server. The control server acts like a coordinator or manager. It decides how the tasks should be distributed among available systems. Next, the control server sends tasks to different grid nodes. Grid nodes are multiple distributed computers connected together in a grid environment. Each node processes a portion of the task independently. The arrows between grid nodes indicate that nodes can also communicate and share information with each other during processing. Finally, after processing is completed, the results are sent back through the system to the user. So overall, this diagram shows how GridSim models distributed grid computing where multiple heterogeneous systems work together to process large tasks efficiently. SimJava. This slide explains SimJava, which is a Java-based discrete event simulation library. SimJava manages simulation events such as sending tasks, receiving tasks, scheduling operations, and handling communication between components. It provides important features like entities, which represent simulation components, event queues, which manage simulation events, a simulation clock, which controls simulation timing. Both CloudSim and GridSim depend on SimJava for handling simulation events and time management. So overall, SimJava acts as the core event management engine behind cloud simulation frameworks. Let us understand this layered pyramid diagram related to CloudSim. At the bottom, we have SimJava. This is the foundation layer and provides discrete event simulation support. It handles simulation timing, event scheduling, and communication between simulation components. Above SimJava is the GridSim. GridSim uses SimJava and adds grid computing functionalities such as grid services and core distributed computing elements. Next comes CloudSim. CloudSim is built on top of GridSim and provides cloud-specific features such as user interface structures, virtual machine services, cloud services, and cloud resource management. At the top is the user code layer. This is where users define the simulation scenario, application configuration, and scheduling policies according to their experiment requirements. So overall, the diagram shows that SimJava forms the base event simulation engine, GridSim extends it for grid computing, and CloudSim further extends it for cloud computing. And finally, users build their simulation experiments on top of these layers. Working platform for CloudSim. This slide explains the software requirements and setup process needed to run CloudSim. First, the system requires Java JDK version 8 or later because CloudSim is developed using Java. An IDE such as Eclipse IDE or Apache NetBeans is used to write and execute simulation programs. Next, the CloudSim toolkit and required .jar library files must be downloaded and added to the Java project build path. After setup, users can start writing simulation code by creating data centers, virtual machines, cloudlets, or tasks and brokers. Finally, the simulation is executed to analyze cloud resource allocation and performance. This slide also explains the basic workflow followed while creating a simulation in CloudSim. First, the CloudSim library is initiated to start the simulation environment. Next, data centers are created to represent cloud infrastructure resources. After that, virtual machines are created to represent computing systems where tasks will be executed. Then, cloudlets are created. Cloudlets represent application tasks or workloads. The cloudlets are then bound to suitable virtual machines for execution. Finally, the simulation is started and the results such as execution time, resource usage, and performance are collected and analyzed. Now let us move to green cloud computing. Green cloud computing refers to designing and using cloud computing technologies in an environmentally friendly manner. The main goal is to reduce energy consumption carbon emissions, and environmental impact while still maintaining efficient cloud services. This concept focuses on building sustainable cloud infrastructures using energy efficient data centers, optimized resource utilization, and eco friendly computing practices. Introduction to Green Cloud. Green cloud computing focuses on designing and using cloud technologies in an environmentally friendly and energy efficient manner. The main aim is to reduce carbon emissions and improve environmental sustainability while operating cloud systems. Major cloud providers such as Microsoft, Amazon Web Services, and Google use renewable energy sources to run their data centers as part of Green Cloud initiatives. This slide also highlights important focus areas such as reducing data center power consumption, minimizing communication network energy cost, and improving server cooling efficiency. Some important features of Green Cloud include detailed energy modeling of servers and networks, analysis of communication energy usage inside data centers, designing energy efficient cloud systems, studying the trade off between performance and power consumption. So, overall, green cloud computing aims to make cloud infrastructure more sustainable, energy efficient, and environmentally responsible. How to make the cloud green? This slide explains different methods used to make cloud computing environmentally friendly. The first method is using nano data centers. These small scale data centers reduce heat generation, lower cooling cost, and provides better scalability compared to traditional data centers. The second method is frequency scaling or dynamic voltage frequency scaling. Here, the processor speed and voltage are adjusted dynamically based on workload demand, which helps reduce power consumption and energy usage. Another important method is virtualization. Virtualization allows multiple virtual machines to share the same physical server efficiently. This improves resource utilization, reduces hardware usage, and lowers overall energy consumption. This slide also mentions that many organizations are continuously developing new green technologies and sustainable practices to improve cloud efficiency while reducing environmental impact. So, overall, these techniques help create energy efficient and eco friendly cloud infrastructures. What are the goals of green computing? The primary aim of green computing is to reduce the use of hazardous materials, improve energy efficiency, and encourage recycling or environmentally safe disposal of electronic waste. It also focuses on designing efficient algorithms and systems that consume less power while maintaining good performance. It also highlights several important areas for achieving green computing: increasing the lifespan of products, improving algorithm efficiency, efficient allocation of resources, virtualization, applying efficient power management techniques. So, overall, green computing aims to create sustainable and energy efficient computing systems with minimal environmental impact. This slide summarizes the cloud simulators discussed in this unit. CloudSim is a flexible simulator mainly used for general cloud resource management and cloud environment simulation. GridSim acts as the foundation for CloudSim and focuses on grid computing simulation. SimJava provides the event management and simulation engine used by both GridSim and CloudSim. Green Cloud mainly focuses on energy efficient cloud and network simulation. This slide also compares CloudSim and Green Cloud. CloudSim mainly focuses on cloud resource management and provides faster simulation because its network model is simpler. Green Cloud focuses more on energy efficient cloud computing and detailed network simulation. Due to this detailed modeling, Green Cloud simulations are comparatively slower. Finally, the slide mentions that CloudSim is built on GridSim and SimJava, while Green Cloud is built using NS2, which is a network simulator. So overall, the choice of simulator depends on the specific goals of the cloud simulation environment. With that, we come to the end of Unit 5 on cloud applications and cloud simulators. Overall, these concepts play an important role in designing efficient, scalable, and sustainable cloud computing systems. Thank you.